Alright guys, so this is a continuation of the previous video in which we have to find the pH of weak acids and weak bases. Specifically in this video we're going to try to find the pH of a weak base. So pretty much the thought process is the same. We have to use an ice table and we have to calculate an X value, and from that X value we have to get our OH minus concentration and all that good stuff. But there is going to be an extra step and one unique characteristic you have to remember when it comes to dealing with weak bases. So in this problem, they tell us that we have 0.10 moles per liter of ammonia, and they're asking us to calculate the pH. So ammonia is a weak base, and we have to, if we're given a weak base, we have to find the pH of it by taking our weak base and adding some water to it. Okay, we have to add some water to it, and you'll see why in a bit when I complete this reaction. So if you're given a weak base, add water to that weak base. So if we have a beaker here, if I was to draw a beaker, really quickly, if I was to draw a beaker, this beaker would contain some weak base and some water, which I'll draw out in some blue. Okay, it'll have some water in it. And the reason why you have to do that is you have to create some hydroxides on the other side. So if I was to complete this reaction, I'll get its weak conjugate base, so NH4 plus some ammonium, plus some hydroxide ions. And the only way I can get that hydroxide is by adding H2O, because one of the hydrogens will bind to the ammonia to create ammonium, and the remaining oxygen and hydrogen will bind to each other to create the hydroxide ion. And this is very important because this will allow us to find a certain concentration of our hydroxide ion, which we can later solve for pH. So we have to keep the same, ideology that we used in weak acids to weak bases. We have to create an ice table. All right? So I'm going to do that. I'm going to create an ice table. ICE. All right, the I stands for our initial concentration. So in this beaker, we have some ammonia and we have some water. Specifically, we have 0.10 moles per liter of ammonia. Now, the water we don't really care about. In equilibrium, we don't really care about pure liquids, and water in this case is a pure liquid. So we don't really care about that because of the state of matter that it's in. And you should remember that from chapter 13 in chemical equilibrium. We don't care about liquids. We don't care about pure liquids or pure solids. So that's why we're not really considering anything with this H2O. And that's also why they didn't give us any information about the H2O. And now I'm going to separate our reactants from our products. And we have ammonia and OH minus as our products. But in our beaker, we didn't really create any ammonia or OH minus. We didn't create any of that because the reaction hasn't occurred initially. So we're going to say 0 moles per liter of ammonia and 0 moles per liter of hydroxide. Now, we have to understand what the change is going to be when the reaction is taking place. So as the reaction is taking place, we're going to be producing more and more product. We're going to be producing more and more ammonia and more hydroxide, and we're going to be producing less and less ammonia because the ammonia is going to be reacting with the water to create the product. So we're going to denote that change as a minus X. We're going to be losing some of our initial concentration of ammonia, and we're going to be gaining a certain amount. We're not sure what that amount is, but we're going to be gaining a certain amount of ammonium and gaining a certain amount of hydroxide. The hydroxide we're especially concerned with when it comes to solving for our pH. So our equilibrium at the end of our whole reaction, what is our expression going to be like for each and every one of these separate entities? Well, for ammonia, it's going to be 0.1 minus X. Okay, we're going to take our initial and our change and create an expression based off of that. For our ammonium, it's going to be 0 plus X, which is X. Same thing with hydroxide. And now we have to create an equilibrium expression. And we have to be very familiar with that from chapter 13 because that's going to be a huge part when it comes to solving problems with acids and bases. So we have to use our our base constant. We have to use our base constant. Why do we have to use a base constant? Well, previously we used a acid constant because we dealt with an acid. Our beginning thing was a weak acid that we had to deal with. It was HNO2 in the previous video. Here we have a weak base. So we have to have a constant for a base because we're dealing with a base. We're dealing with the reaction of a weak base. So our Kb should be given to us, and if it's not given to you, it should be in the back of your book if this is a homework problem that was assigned. But our constant, our base constant for NH3 or for ammonia is 1.8 times 10 to the power of negative 5. It's 1.8 times 10 to the power of negative 5. And that will be equal to our reactants, our products over our reactants. Our products over our reactants, and that's going to be X times X. This is going to represent our ammonium, and this is our hydroxide, over 0.1 minus X. 0.1 minus X. Okay, and we can simplify this as X squared over 0.1. Now, why am I just saying that our bottom, our denominator, our reactant is just 0.1? Well, I'm making a 5% assumption that I talked about in the previous video. I make this 5% assumption. I assume that our reactant is going to be approximately 0.1 because our Kb value is so small. It's 1.8 times 10 to the negative 5. It's really, really small. So we know that whatever X value we're losing here is going to be so small that we can approximate that our concentration at the end of our reaction is going to be approximately 0.1 moles per liter, give or take a little bit. So we're going to make that approximation because of a small Kb value. And this, of course, is equal to 1.8 times 10 to the negative 5. So if we do some algebraic manipulation here, we multiply both sides by 0.1 and take the square root of that because we have X squared. We should get X to equal 0.0013. That should be equal to what our X is. If we multiply both sides by 0.1 and take the square root, instead of getting X squared, we should get X. So we take the square root, 0.0013. And because we made an assumption, we want to make sure the assumption's valid. So we have to divide it by our initial concentration of the thing we made an assumption based off of. Well, the thing we made an assumption based off of is ammonia. So we have to divide it by our initial concentration of ammonia, which is 0.1 moles per liter, and multiply that by 100 to get a percent value. And that percent value is approximately 1.34%. So that percent is far less than 5%. That's why it's called the 5% assumption. So if it's less than 5%, the assumption's valid. The margin of error is very small. But if it's greater than 5%, then our margin of error is it's a little too high than what we want it to be, so we have to use some quadratic manipulation in order to solve for X, which is a little bit more tedious. But because our assumption is verified with this 5% test, and because it's lower than 5%, we know that our 0.0013 for our X value is valid. So what does this tell us? Well, we know that our end expression for our reaction is going to be X and X. We solved for X here. We said that X is equal to 0.0013. So we pretty much solved for the concentrations of NH4 and OH minus, NH4 plus and OH minus, ammonium and hydroxide at the end of the reaction. So if I was to draw another beaker at the end of this reaction, it would not only contain some NH3, of course we lost some, but it will still contain a little bit. It'll contain some NH3, but it'll also contain some product. It'll also contain some NH4, some ammonium, and some hydroxide. And that amount is X, which we solved for. So the amount of hydroxide we have in this beaker is going to be 0.0013 moles per liter. And the amount of ammonium we have in the beaker is going to be equal to X, which is 0.0013 moles per liter. Now, we're mainly concerned with the OH minus because they ask us to solve for pH. So we know that our OH minus concentration is 0.0013 moles per liter. So to find the pOH of that, we can just take the negative log of our concentration of OH. And our pOH should be It should be, and if I type this into my calculator really quickly, the negative log of 0.0013, it should be approximately 2.889. It should be about. So our pH, which is the thing that we need to solve for, our pH will be equal to 14 minus our pOH, and that's because the pH scale ranges from 0 to 14. So if we want to solve for pH, we do 14, the maximum of the scale, minus our pOH, which we got to be 2.89. And if we do 14 minus 2.89, we should get a pH of 11.11. Okay, and this makes a lot of sense because while this reaction is happening, we're producing a lot of OH minus ions. So in this beaker, after the reaction has finished, we're going to be having some OH minus ions. And that makes the solution that we have, and keep in mind that this beaker, I forgot to draw it, but keep in mind this beaker has some water. So this solution is going to become very basic because you're producing OH minus ions here. You're not producing H plus ions. In the previous problem you were, and that's why our pH was below 7. It was slightly acidic. But here we know that we should get a pH that is basic, that should be greater than 7 because we're producing OH minus ions. So that's how you solve for our pH. We simply make an ice table, and we have to do an extra step by subtracting our pOH by 14 in order to get our pH. And also keep in mind, this is very, very, very important, you have to add your weak base to H2O in order to create some hydroxide ions. Alright, so I hope that this video helps with better understanding of how to deal with weak base problems, and I hope that you tune in for more. Thank you.